Good afternoon, everyone. Thank you for coming to my talk. I'm Zihao Zhan. I'm currently an assistant professor from Texas Tech University. Today, I'm going to present my work, VoltSchemer use voltage noise to manipulate your wireless charger. This work is completed with my colleagues from University of Florida and the CertiK. So wireless charging is a new technology that's becoming increasingly popular in our daily lives. Unlike wireless charging transfers power through magnetic coupling instead of electrical connections. This method is not only convenient, but also safe, reducing the need for cables and keeping things clutter-free. So how does wireless charging achieve this? First of all, wireless charging systems must comply with the Qi standards, where bidirectional Qi communications are used to implement the techniques like feedback control and foreign object detection. They use in-band communications with chargers manipulating the power signal's frequency, and the charged device modulating its amplitude to exchange messages. Wireless charging is typically considered power transfer only, with the data exchange only between the charger and the charged device. The adapter's only ability is supplying the DC voltage. So it's considered that even compromised, its influence would be minimal. However, we challenge such assumptions by introducing VoltSchemer, which shows that by only manipulating the voltage, we can take full control of a wireless charger. To explain how VoltSchemer works, we first need to understand how the EMI on the power adapter can affect the signals on the load, and in turn, how the load operations can affect the signals on the power adapter. To analyze how the electromagnetic interference propagates from the adapter to the load, we break down the system into three key parts and calculate how an interference signals with varying frequencies and amplitudes impact the TX coil current, which is proportional to the magnetic field used to transfer power. And due to the time limit, we are skipping the derivation details, and the results show that the TX current is amplitude modulated by the input voltage signal. The modulation depth is attenuated by a factor K, which with higher frequency signals experiencing greater attenuations. However, upon further examination, we discovered that the critical weakness, the system fails to adequately attenuate low-frequency signals, such as those lower than 10 kHz. We also analyze how the load operation affects the signals on the power adapter. When the load changes, voltage fluctuations are induced but quickly stabilized on the power adapter, which is equivalent to the effect of filtered by the derivative of an impulse function. As for the frequency shift-induced signals on the power adapter, the system shows high attenuations for signals around that 140 kHz power signal, reducing the voltage amplitude to around 10 millivolts, making those features invisible in the time domain traces. So with this analysis, it can help us better understand what an attacker can achieve by controlling the input voltage of the wireless charger. Firstly, an attacker can amplitude the power signal, and also given that the ASK modulation frequency is 2 kHz, VoltSchemer can modify ASK packets, effectively controlling the communications from the power receiver to the charger. To verify this, we show a simple example where we can inject the voltage noises forming control error packets, which can trick in the charger into adjusting the charging rate. And the analysis of load to adapter EMI propagation also help us in designing methods to eavesdrop on Qi communications. By applying a filter that can counteract the derivative of the impulse function, we can recover clear ASK patterns from the modulated magnetic field and retrieve the messages sent to the chargers. And for the FSK modulation, although the signal is too weak to be visible in the time domain, we found that the power signals lies in a very clean frequency band, making the FSK patterns apparent in the frequency domain, as shown in this spectrogram. And this allows us to recover the messages sent by the charger. So because VoltSchemer only requires manipulating the output voltage, we don't even need to fully build a malicious power adapter to implement the attack. Instead, a simple voltage manipulator can do the job. So this device can inject AC signals by controlling MOSFET switches and can be easily installed by plugging into a genuine power outlet. And the commercial off-the-shelf wireless chargers connected to the camouflaged power port can be compromised. Now let's see attacks an attacker can achieve with VoltSchemer. So the first attack is voice assistant manipulation. There is a previous research demonstrating that an AM modulated magnetic field can induce sounds in a microphone and controlling the voice assistants like Siri. However, their method requires a malicious wireless charger with malicious MCUs and can't work with off-the-shelf chargers. VoltSchemer can simply control the input voltage of those commercial off-the-shelf chargers to modulate the magnetic field and achieve the same effect. To demonstrate this, we tested two voice wake-up commands by adding them to the charger's input voltage while smartphones were wirelessly charging. Although the signal-to-noise ratio is lowered, we find the distinctive features are still preserved, and the voice assistants can still be successfully waken up. And our second attack scenario is called wireless power toasting. Normally, a feedback control ensures a safe wireless power transfer. For example, when the charging power is too high, a smartphone can send a control error packet to the charger, telling it to decrease the charging power. However, VoltSchemer can corrupt the packet and inject a synthesized one that tricks the charger into increasing the charging rate instead. Simultaneously, the smartphone may also report its received power to the charger, which may indicate the charging efficiency is low. And similarly, VoltSchemer can also corrupt this packet and deceive the charger into believing the charging efficiency is high. And as the temperature continues as the smartphone continues to overcharge and overheat, it triggers the first protection mechanism, shutting off the charging module and sending an end power transfer packet to the charger. However, this packet can still be corrupted by VoltSchemer. So from the charger's perspective, everything seems normal, so it continues transmitting power at a high rate and causing the smartphone to continue heat up until the second protection is triggered, which closes all apps and disables user interactions, but the temperature continues to increase. When the temperature reaches approximately 170 Fahrenheit, the smartphone triggers the third protection mechanism, resulting in a complete shutdown of the device. While all these protection mechanisms aims to minimize the heat generation by the smartphone itself, they can't stop the charger from transmitting power. So despite the shutdown, the charger continues to heat up the phone to a high temperature to around 178 Fahrenheit, which poses serious risks such as battery fire or explosions. And our third attack scenario is foreign object destruction. Normally, a wireless charger won't transmit power to a foreign object for two reasons. First, starting power transfer requires interactive communications, which a random foreign object cannot complete. Second, the foreign object detection technique in the charger will stop charging when detecting lower Q factors caused by a foreign object. However, our VoltSchemer can both receive and send key messages to achieve such interactive communications with the charger. This allows us the power adapter to mimic as a legitimate power receiver and trick the wireless charger into transferring power. The FOD mechanism can be easily bypassed by providing a lower reference Q factor in the FOD packet. Then all transferred power is converted into heat, causing the object to heat up significantly. This can lead to severe damages, such as causing the vehicle key to explode and making the USB drives unreadable. So in our evaluations, we tested VoltSchemer on 9 top-selling commercial off-the-shelf wireless chargers. For the voice assistant manipulation attack, we tested 2 voice assistants using 6 different voice commands. We evaluated the attacking distance and the required interference intensity for successful attacks. Most attacks can succeed with a low interference level, though the effective attacking distance are typically under 10 centimeters, it's sufficient because smartphones must be put directly on top of the charger for charging. In the wireless power toasting attack, we monitored the temperature rise and the triggered protections of the smartphones. The results show that higher power chargers lead to more severe consequences. For the foreign object destruction attack, the evaluation demonstrates that VoltSchemer can command all chargers to heat up and destroy foreign objects, with higher power chargers causing greater destructions. Overall, our evaluation underscores that the effectiveness and the broad applicability of VoltSchemer. We propose two potential countermeasures. First, adding an extra DC-DC converter can provide high attenuation, especially at the low frequencies, as demonstrated by our measurements. However, this solution also comes with an increased cost, which could be a concern for the manufacturers. Second, using out-of-band communication channels can make Qi communications more reliable. However, in addition to adding cost, this method may also affect the device compatibility by requiring power receivers to incorporate extra communication modules. So in conclusion, our VoltSchemer tech demonstrates that by simply manipulating the voltage, it is possible to fully control the wireless charging system, as all off-the-shelf wireless chargers that conform with current EMC standards are susceptible. We believe that these standards currently fall short in preventing IEMI attacks, and they may need more updates in the future to better protect electrical systems. And thank you for coming to talk. Do you have any questions?